Thank you, Hongxin. Hello, everyone. It's a pleasure to present our work. Actually, in this work, we are using system approach to look at SDN controllers. We are detecting the control policy violations through the software method. Yeah, this is a collaboration with Beihang and Zhonghua. First, we know the software-defined network is an interesting technology. It actually shifts the control out of the network and make the control separate so that it have more flexibility. So the network device is divided into control plane and data plane. So the control plane receive message and decide how the traffic can flow, and the data plane forward the messages. As we always see, our flexibility is also attackers' flexibility. So they can leverage on this flexibility to manipulate the control planes. For example, they can send a message to modify or deactivate network forwarding and change security policies. For example, if they fake IP address and send to the controller and let the controller to learn wrong information about network, it will have bad consequence on the network. So related work to detect this CPM defense include a few categories. The first one, do anomaly detection. They create rules to decide what are the regular open flow rules. If there are bad open flow rules, they can detect the attack. But some of the attack doesn't need to go through the open flow rule changes. Actually, they through other packets affecting the states of the control plane. Right? So suppose if a control plane has some software bug or vulnerability, that can be affected by the data packets. So for this kind of attack, it cannot be detected by the rules. And also another line of approach is using the policy verification. They validate the policy on the control plane are all in good shape, but for some attacks, for example, to do the link verification, they are follow the policies, but they use the regular functionality to do attacks. Why this existing work cannot see those attacks? We noticed that one of the problems is that the control plane manipulation, the policy manipulated, is not effected through the policy changes, but instead they are happen on some other operations. But based on our research in the system and the software domains, we realized that a lot of the operations on certain functionality actually can be reflected by the contextual operations happen in the same software. Translate to this domain is actually the controller operations provide insights into the network state changes. As SDN is a software-defined network, it's just another software system. For example, the network SDN controller operates on the open flow messages. The messages actually defines what are the states the controller is in, and the affects its view about the network. And also how the control policy is changed also can be reflected by how the software operates. So we put this together based on our experience in software system and system security. We believe that the provenance graph actually provides a way to describe the causal dependency between the functions in the SDN controller and thus in the control plane. So based on the idea, we want to migrate our success in the software solution into the SDN controller. But the main challenge is that how do we extract features for very long-running CPM attack and many CPM message and operations? Even if we build a graph, the graph will be huge. If we partition the graph using using regular boundary, for example, we just do the regular behavior subgraph partition. Actually, during the long time between the attack change the control plane and the attack is detected by the user, it's actually very difficult to have a clear subgraph. Typically, a subgraph is the boundary is blur and the graph is large. Our solution is actually we use the multi-state features. We detect the single features in different states and chain them together as a smaller subgraph. Also, how do we decide the similarity and what is a good behavior or bad behavior? A simple solution is just focus on the fixed hop graph features. The problem there is that typically that is not good enough to reflect the similarity. And in the solution, based on our experience, actually we propose to use the context in the path we find as a way to define semantics. So putting this together, we have an approach we call the ProvGuard. Use it to detect the CPM on the SDN network based on the provenance graph. First, we do provenance. We instrument the SDN controller, the Java, in our particular example, we instrument the Java program source code to get enough information to describe the operations of the controller. So these logs are built provenance graph using the traditional provenance graph building approach. And based on that, we do the semantic deviation evaluation and detect the suspicious behaviors. So the first step is actually we need to analyze the SDN controller and decide where are the points we want to hook. We capture the data plane message operations, and we analyze the source code and identify those instrumentation points and take logs out of it. After log is taken, we construct a graph to describe its behaviors. Notice that in the log, one of the problems is that it has many events, and few events is related to the key operations that can affect the control plane. So our idea is that we construct the graph based on the execution unit. Is a concept. For example, if you have many threads in the software, if you build a very complete graph, it can be mixed together. And all the data flows mixed together, you have a state blown up. One of the typical solution is that we identify the threads or the processes inside the software. This way, we can prevent the data flow from being mixed. We call each thread is an execution unit. We construct the execution unit graph and find the dependency and also find the connections between the different execution units. For example, two of them may have to share the same attribute or they have some data connect together. Then we reduce the unnecessary edges that is not related to the data flow operations to make sure it's our key message is not hidden among a lot of noises. After we have the graph, we extract path. We use the subpath inside the execution graph as the subgraph. Then we associate these attributes or data together to form a connected path among the small pieces in different execution units. Eventually, we get a graph represented as a long chain or long path of operations. It actually captures the operations related to the CPM operations. So that is a data operation that can have impact on the control plane messages. Based on this representation, potentially we have different ways to see how to represent the normal behavior or how to represent the malicious behavior. In another line of background research, actually we learned that typically when processing a complete graph, the neighbor nodes provides the context to review its semantics. Here actually we use a similar idea. We use the context in the past to offer the semantics and use that to do the detection. After we have the whole system, we prototype the system and implement it on the Floodlight SDN controller. It's a Java-based. We do the instrumentation and deployment. We use the mini-net network simulation to generate data and collect logs. During the data collection, we have the normal one, and also we tried 4 types of typical CPM attacks. In the evaluation, we evaluate how effectively the ProvGuards can detect these attacks. And then we evaluate the effectiveness of the noise redundancy reduction. And also we see how the contextual semantics contribute to the anomaly detection. And then we also see how our efforts reduce the workload and what is the overhead. So talk about the effectiveness. Well, we found that ProvGuard effectively captures these features and perform better than other solutions on 4 types of attacks. Actually, basically, it proves our idea. The operation context provides semantics, which in turn can reflect the malicious behaviors in SDN attacks. And also, we check the resilience of the path, the reduction. We try to scale and to different networks, although basically by injecting a lot, effectively it's actually injecting a lot of noises. And we found that our algorithm select the core signals is stable enough to be not affected. And also we tried how the actions, how the context helps by giving different windows of operations. As you can see at the bottom, when the context is low, we can have more errors, and we have more context, it's become more accurate. Also, we tried to measure the workload assigned to the investigators. Then we find out only a small portion of the edges need to request manual review. Others we can assign meanings and detect the attack. And in terms of performance, we found that the RTT average between 1.8% or 24% over the regular uninstrumented controller. And roughly the log data cost 1.3 GB per hour storage overhead. This one is a bit high, but I believe there are spaces for further optimization. So in summary, this is our interesting attempt to use a software security technology on network security. By using provenance to the SDN controller, we review the meaning of the SDN control plane operations through the watching how the data plane operations works. And this way, we have a more reliable way to summarize the attack semantics and detect attacks. Thank you.
Any questions from audience? Okay, so yeah, I have questions. So yeah, for the implementation, you will focus on Floodlight. So have you think about even other controllers? I know there's some other controllers. Okay, even Open Daylight. So what's when you implement those in those controllers, there's any differences? Okay.
Oh, there can be a difference, but I think the technique is general. So this one we definitely do manual analysis, and we believe that there's a way by certain principle we can analyze other controllers to plug in the logging points. I think maybe one of the interesting success stories is Trent. Trent used to have a paper to analyze the Linux kernel source code and automatically detect the Linux secure module hooks place. I think a similar idea or technology can potentially be used in this domain, finding all the important locations for the SDN controller's data plane operations.
Okay. Another question. So for this attack, actually, so exactly we can do intrusion detection. So do you think there's any other suggestions we can prevent from design perspective? We can directly prevent such attack happening in SDN environment. Yeah.
Right. I think this, in general, is to talk about the SDN operation, the control plane logic integrity. So we are preventing the control plane logic from being affected through other means. Basically, if we turn on this approach, it actually can detect the hidden semantics so that we can channel the hidden semantics back to the like the policy-based or rule-based detection, make it visible. Okay, thank you. Okay, thank you. Thank you.